Hello, my name is Luke Ditria. This video is here to present my FYP project, the ORVI, Object Recognition for the Visually Impaired. The following poster was on display at the 2016 Spark. The significant contributions for this project are the design and construction of a compact device that can perform real-time image processing, the design and implementation of software to allow real-time object locating on a small, low-powered CPU, the design and implementation of an algorithm to increase the robustness of object locating, the implementation of object tracking using optical flow, the design, construction, and implementation of Micro Coil Actuators as a new form of haptic feedback. For those living with visual impairment, living an independent life can be tricky. Though there are a number of services, such as seeing eye dogs, and devices like the walking cane, finding a landmark or shop front that is unfamiliar can be impossible without someone to help. The aim of this project is to create a small handheld device that will allow a user to find a specific location, building, or landmark in their general area. This device would give directions to the user, which they would then use with pre-existing methods, such as the cane or seeing eye dog, to navigate towards the desired location. The software would use an image from Google Street View as a reference for the real world. Someone living with a visual impairment would use the device when they wish to visit a new shop located on a shopping strip close to home. They've been to this general location before and, with the use of their guide dog, can comfortably get to the street on their own. The problem arises in the next step, locating the unfamiliar shop on the street they are on. Without someone to help, it may be impossible to locate and enter the shop or building. This is where the ORVI can help. The user, or a friend or helper, would go into Google Street View and navigate towards the shop. Once they have found the shop they wish to visit, they would then take an image of the shop front and upload this onto the ORVI device. When they are in the general location of the shop, they can slowly sweep the ORVI device back and forth. If the ORVI recognizes the shop front, it will start directing towards it. They can then use their guide dog to navigate towards the shop. The ORVI is made up of several crucial components, each of which must be carefully chosen to allow for the optimal performance of the device. These components must then be arranged in the device to create a simple and portable handheld package. At the heart of the ORVI is the Raspberry Pi Zero module. A number of small computer modules were researched and compared with a number of key parameters, such as power, cost, and physical size. The Raspberry Pi Zero was chosen because it is suitably powerful and cost-effective, as well as being small in size. It also has a camera port and GPIO pins, which are necessary for the ORVI to work. The Raspberry Pi V2 8-megapixel camera module was chosen because it can easily connect to the Raspberry Pi Zero module. Its small size, low cost, and the wealth of online support make it favorable for use in the ORVI device. To direct the user, a source of haptic feedback will be required. This haptic feedback will need to be localized in order to direct the user left, right, up, or down, and towards the object. There are currently a number of sources of haptic feedback that are available, such as piezoelectric stack actuators, vibrating motors, voice coil actuators, and solenoids. Despite this, through research and testing, it was determined that none of these commercially available actuators would be suitable. This was either due to their size, cost, or the fact that they did not produce a localized source of feedback. It was therefore decided to create a custom micro actuator array that would be tailor-made to fit the ORVI device. A number of iterations were designed, and thanks to the help of 3D printing, were tested. Here we see the first generation of a functional micro coil actuator. All initial designs worked using the same basic principle. A stationary coil and a magnet were used to create motion. When a current is applied to the coil, the resultant magnetic field would push the magnet and the pin, creating movement that can be felt by the user. In the final design, the position of the coil and the magnet were changed, and a single magnet was used for the array of 4 actuators. These 4 actuators are used to tell the user if the object they are looking for is to the left, right, up, or down. This micro coil array module is then embedded into the ORVI device. Because the output of the GPIO pins from the Raspberry Pi can only supply up to 16 mA, a control board was needed to boost the current into the coils. A small board was designed to fit 4 SMD and channel MOSFETs. These MOSFETs would act like a switch to turn on and off the coils. The enclosure for the ORVI device was also 3D printed. The enclosure had to house the battery, camera, Raspberry Pi, charger, actuators, and other hardware. It also had to be designed and printed in pieces to allow for assembly after printing. The ORVI will be running custom-designed and implemented image processing software, which will be used to locate and track a reference object in the world. The obvious choice for image processing software was to use OpenCV, an open-sourced computer vision library. The ORVI will be programmed in C++ to aid in efficiency and speed. Using OpenCV as well will drastically speed up the time taken to write the image processing software. As the processor on the device is small, code running on it will have to be as fast and efficient as possible, or the device will not be able to provide real-time feedback. The ORVI device will be held by the user who will be using it in real time. This will introduce many transformations to the object image as seen through the camera. These transformations include skew, stretch, and rotations caused by the position and heading of the ORVI in 3D space. Therefore, the object in the reference image may not be the same orientation as what it appears in the world. Because of this, any key point detection used must consider various possible rotations. ORB, or Orientated Fast and Rotated Brief, feature detector and key point detector does just this. ORB uses fast feature detection on image pyramids to find key points. Fast works by running through the pixels of the image till it finds a corner or edge, which it will determine as a key point or feature of the image. A pixel is determined to be an edge if a certain number of continuous pixels specified by the user in a ring around the center pixel are greater than or less than a threshold value. To combat rotations in the image, ORB calculates the intensity-weighted centroid around the best features, and uses this as the orientation for the image patch. This is done by calculating the direction of the intensity gradients in a patch around each feature. ORB uses Brief to calculate descriptors once it has located key points. Brief takes a small image patch around a feature and compares the intensity of pairs of pixels within this patch. This generates a number of binary outputs. For example, if this pixel is greater than this pixel in intensity, the output is 1. If it is less than, the output is 0. Once descriptors for every key point in both images have been calculated, descriptors then must be compared and matched based on their similarities. FLANN, the fast library for approximate nearest neighbors, is a very fast method for comparing in high-dimensional space. Such is the case when matching features. To aid in subsequent stages, it is important to filter out low-quality matches. We can do this by using the distance between matched key points. One way to do this is using the ratio test, which uses the ratio between the best match and the second best match. If there is a large difference between the score of the best match and the next best match, then the best match can be said to be unique, as the best match is better than the next best match by a large amount. In addition to this, a dynamic ratio threshold is used. This works by specifying a number of matches we would like to keep, and then adjusting the ratio value to achieve this number of matches. This is more beneficial over a static ratio threshold, as it allows for the selection of an optimal threshold for a dynamic system without having to calculate and sort the ratio of every match. The homography matrix needs to be calculated next. The homography relates the perspective of the object image and the scene image. It can therefore be used to project the object image into the scene. In the ORVI, it'll be used to project the center of the object into the scene image. This will be used as a prediction for the location of the object in the scene. The homography matrix is calculated using the matches found between features in the previous steps. Even though we have done some filtering on the matches, it is likely that there are still a number of false matches which will affect the accuracy of the homography calculation. Therefore, RANSAC, or random sample consensus, is used to find the consensus between all the matches for a calculated homography. This can be done because to calculate the homography between two images, you only need 4 matches. Because it is unlikely that those 4 matches will be 100% correct, we use RANSAC to randomly select 4 matches and then calculate the homography. The calculated homography that best fits the most matches is selected as the predicted homography and can be used to transform the object into the scene. The more matches we use to calculate the homography, the more likely we will get an accurate homography. But as we increase the number of matches we use to calculate the homography, the time it takes to calculate the homography matrix will also increase. In order for our software to run in real time, we must therefore forfeit the number of matches we take into calculating the homography matrix. Because of this, the homography calculation may not be as robust as it could be. To increase the robustness of the predicted center of the object in the scene, you must therefore use additional methods. A scoring system is implemented based off how often the object is projected in the scene at a specific location. If long runs of previous projected centers have a low variance in their XY coordinates, that is, they fall into the same general area, a new scored projected center is created. This scored projected center is remembered, and every time the real projected center falls within a threshold of the scored projected center, the score of that projected center is increased. A different scored projected center can be created if a run of real projected centers with a low variance is longer than the current scored projected center. Finally, object tracking is implemented using optical flow. The scored projected center calculated from the real homography projections of the center of the object into the scene is what is used in combination with optical flow to track the predicted location of the object in the scene. The relative motion of the scene is calculated with optical flow by taking a large number of points and then predicting their future location in the next frame. The median change in XY positions in each of these points between the current and future frames are then used to move the scored projected center. The result is the ORVI, a small, simple to use handheld device that combines the image processing and hardware discussed previously into a truly unique device. Future work. Potential future additions to the device that could aid in the ease of use, such as the addition of Bluetooth and Wi-Fi, should be considered in further iterations. Also, the addition of software to aid in acquiring of relevant Google Street View images would be beneficial for users. This could also include the creation of a smartphone app. Thank you for viewing this video presentation of my FYP project, the ORVI, Object Recognition for the Visually Impaired.